These are the solutions to recitation activity 8. So this question is asking us to consider the effect of resonance in the carbonate ion, which statement is true. So let's think about the Lewis structures we can write for CO3 2 minus. So I have 4 valence electrons for carbon, 3 times 6 for the oxygens. Let's add 2 valence electrons for the 2 minus charge. That takes us to a total of 24 valence electrons. So I can sketch one Lewis structure where I have, I might start with 3 oxygens single bonded with lone pairs on each. That's all 24 of my electrons, so no lone pairs left over for carbon. And so then the only issue here is right now I have a formal charge of plus and minus for carbon and oxygens respectively. So why don't I make a double bond? So I move an electron pair off of one of the oxygen atoms in to make a double bond. I end up with this structure here, so those electrons are now moved into a double bond. But then those electrons can resonate over to the other oxygen and then to the other oxygen. And then these electron pairs resonate at all times. The effect of resonance is that if I could sketch these 3 Lewis structures, that the real molecule will look like the average of these. So the average of those structures would look something like this, where we have our carbon, oxygen, oxygen, and then we split that bond across all 3 of the bonds at any given time. So each of the carbon-oxygen bonds has at least that single bond, and then it's getting that extra double bond to about 1/3 of an extent. So these bonds here are about 4/3 bonds, meaning we're sharing 4 bonding pairs of electrons across those 3 carbon-oxygen bonds. So we have 1, 2, 3, 4 bonding pairs of electrons spreading across those 3 covalent bonds. And so the idea here is that all the bonds in carbonate are going to be equal in length. Okay, so all the bonds in carbonate are equal in length. Now, bond length's a complicated property, but generally speaking, you would expect this to probably be a little bit shorter than an ordinary carbon-oxygen single bond and probably a little bit longer than an ordinary carbon-oxygen double bond. So if you're looking at a bond in like methanol, where you get this carbon-oxygen single bond, you have the bond in like carbon dioxide. So this bond here is probably the shortest. This is probably the longest. And then carbonate's bond of about 4/3 bond order will be somewhere in the middle. So the more bonding pairs of electrons, the shorter the bond. But all 3 of these bonds should be equal in length. All the oxygen atoms here turn out to have the exact same charge too. So if you think of the charge of oxygen here, the formal charge we'd expect for oxygen would be minus 2/3. So we're going to share that negative charge. So if you think of any one of these Lewis structures, let's look at the first one. We have our formal charges of carbon and oxygen with the double bond are 0 and 0, and then the 2 oxygens are negative. So we're spreading that negative charge across the 3 oxygen atoms simultaneously. So the charge in the oxygen atoms ends up being the same as well. So minus 2/3 across the 3 atoms, 0 on carbon, all those sum up to be minus 2, the charge on carbonate. Question 2, which molecule below has a linear molecular geometry? So a molecule can be linear when we have 3 atoms, and then when we have 3 atoms with a geometry that doesn't have a set of lone pairs or multiple lone pairs, it's going to kick it into being bent. So whenever we have like a molecule that has 3 total atoms, like an AB2 or however it is that I have 3 total atoms, where the molecule will either be linear or bent. Now it's going to be linear in the case of things like CO2, CS2. So this molecule here is linear. How do I know this? Well, I know the Lewis structure here. If I try to determine the Lewis structure, 4 plus 2 times 6, 16 electrons. So I start carbon, 2 sulfurs, lone pairs are on the sulfurs. And then I have a 2 plus formal charge. I have minus formal charges. So let's make double bonds. And so make another double bond, and we kick these formal charges down to 0 and 0, and our formal charge in carbon is 0. And so my best Lewis structure for CS2 will have two double bonds between carbon and sulfur, and then having two uh, total domains, no lone pairs on carbon, that kicks us into a linear electron domain geometry and a linear molecular geometry. Now, if I look at O3 or N3 minus, or actually, let's look at O3 first. So for O3, I have 18 electrons, 3 times 6. So when I do my Lewis structure, I have a central oxygen. And if I think of putting these two oxygens here, I'm going to intentionally sketch them linear because I'm not thinking of geometry when I'm doing my Lewis structure. I'm just trying to figure out where are my bonds, where are my lone pairs. I do this, I see I have 16 electrons here, so I have 2 electrons left over to put onto this central atom. Now, these electrons, of course, are negatively charged. Dots here are negatively charged. So the bonds, the bonding pair electrons and the lone pair electrons repel each other. So that's going to kick this into a trigonal molecular geometry. And of course, we're going to have resonance taking place here too. We're going to form a double bond. It's going to resonate with this bond over here. So we're going to end up with something that looks like this. We're going to have a bond. We're going to have that extra bond being shared. And we definitely have a nonlinear bond, meaning this bond here is certainly not going to be 180 degrees. It's going to be closer to 120, in fact, slightly less than 120 degrees, because these electron pairs here are going to repel those bond pairs even more, pressing that bond together. So the real bond in ozone is probably going to be like 115, 116 degrees, something along those lines. So certainly not linear. What about N3 minus? Well, now I have 3 times 5 plus 1, that's 16 electrons. So this probably is going to be linear because I have a central nitrogen, connect my 2 nitrogens, lone pairs, no electrons left to go on nitrogen. So nitrogen doesn't have any lone pairs. This is that Lewis structure we were looking at before where we make a double bond, then we make a triple bond with one of the nitrogens, and then we leave, oh, I'm sorry, that would not be the best Lewis structure. Let's start this over again real quick. So we took the 2 electron pairs in, made a double bond, that's good. And then we take another 2 electrons over here, make another double bond, that's good too. We end up with minus and minus, and we end up with a plus formal charge in the central nitrogen. But the key is, regardless of how many bonds you're sketching around, whether you go a triple and a single, or 2 doubles, or even if you make the mistake and think it's a double and 2 triples, or excuse me, a double and a triple bond, which would be wrong because we can't expand the octet of a central atom in the second row. So when you look at the structure here, this Lewis structure here would be categorically wrong. But even if you think this is the right Lewis structure, you're still thinking this molecule is linear. So B and C are linear, but A is not. And so this is categorically wrong, though. So we cannot expand the octet of a second row atom. Question 3, which molecule has a trigonal pyramidal molecular geometry? So trigonal pyramidal molecular geometry comes up within tetrahedral electron domain, where if you imagine having a central atom, let's call the central atom just A. So if we have an AB3, we have 3 things attached to a central atom. I have a lone pair in one of my spots, and I have my B, my B, and my B. This is what a trigonal pyramidal molecule looks like. So I need to have 1 non-bonding domain plus 3 bonding domains. Now these domains here, these can be double bonds, they can be single bonds, they just have to be 3 bonding domains. So we're looking for an AB3, so we can roll out CO2. We already saw like things like CO2, and CS2 from the previous example. So we've seen things like this. This is a linear molecule, and it also doesn't have the right number of atoms to possibly be in the electron domain geometry trigonal pyramidal. Same thing with SF2. This can't possibly be the answer. SF2, 3 total atoms, it's either linear or it's bent. And this molecule turns out to be bent. If you look at it, it has 2 lone pairs on sulfur, the 2 bonding domains to fluorine, so that has to take a bent geometry within tetrahedral. SF6 doesn't make any, or excuse me, SF4 doesn't make any sense either because we have too many atoms. So SF4, the question would be, is it tetrahedral? Is it seesaw shaped within trigonal pyramidal, which that's actually what its shape is, or is it going to be, if it has two non-bonding domains and the four bonding domains to fluorines, then it could possibly be square planar with an octahedral. So the possibilities for SF4 don't include the possibility of being trigonal pyramidal. So the only two possibilities would be ClF3 and ClO3 minus. So let's look at ClO3 minus first. So that's 7, 3 times 6 plus 1. And so that's 18 plus 8, that's 26 electrons. And so we have our central chlorine, our 3 oxygens, lone pairs on the O's. And that's only 24 electrons, so the 2 electrons left over place onto the chlorine atom. So now chlorine's octet's filled. It does have a positive formal charge. Its formal charge is 7 minus 5, which is plus 2. And so we could make 2 double bonds if we wanted to reduce the magnitudes of formal charge, or we could just leave the formal charges as is. Now, in the terms of determining molecular geometry, it doesn't matter if you're making double bonds or not here. If you stay with this Lewis structure, or if you want to make 2 doubles and 1 single, you still are going to be in this electron domain geometry of having 1 non-bonding domain, so that's our lone pair, 1 lone pair, and our 3 bonding domains. So ClO3 minus is the answer to the question, and then just to make sure ClF3 is an incorrect choice, ClF3 would have a total of 4 times 7 for 28 electrons. So we'll have a central chlorine, 3 fluorines, 8 around each F. And of course that uses all but 4 electrons. So we have 2 electrons left over that go on to chlorine. So now I have 2 non-bonding domains, 3 bonding domains. And so this here is within the trigonal bipyramidal electron domain geometry, and this takes that T shape. So it actually would be a shape similar to what we've sketched here. The lone pairs, if we're in this T-shaped geometry with the bonds in the plane of our paper, those lone pairs are kind of coming out towards us and away from us. So these electron pairs are really coming in this direction here. Maybe hard to picture, but they're just 120 degrees relative to the fluorine sticking straight out of the page. All right, what's the electron domain geometry and molecular geometry name for BRF5? So that's 7 times 6, 42 electrons. So bromine, 5 fluorines. I'm just going to sketch one of them because all the other 5s look the same in terms of the electron pairs. And so that's 40 electrons because that's 8 around each of the 5 fluorines. That leaves 2 electrons left over to be placed onto bromine. So bromine has 5 bonding domains. So 5 bonding domains plus 1 non-bonding domain. That's 6 total. 6 total is octahedral. So octahedral domain. And then we just pick one of these spots to put a lone pair. And so let's choose a spot here to put our lone pair. And then we put our fluorines here. And so these fluorines here, like this, the ones I'm circling, are all 90 degrees relative to each other, or approximately 90 degrees relative to each other in a square plane. And then we can make a pyramid with this fluorine here. And so we make a square pyramid. And so if you try to picture the shape and try to think of what the name that the shape represents, the key here is when you do experiments, like you can do an experiment to see where nuclei are using like X-ray diffraction, you can't really see where the electrons are, they're too small. And so that's why we give a different name for the molecular geometry name compared to the electron domain geometry. Now the two are inherently linked. You have to kind of link up the electron domain geometry to the molecular geometry so they are inherently linked together. But for the molecular geometry name, you're just trying to name what's the shape of the atoms, what's like the atom geometry. It's the same shape you get from octahedral. It's just you kind of take the electron pair, the atom away from one of the octahedral spots with a lone pair, and then name the shape that you get from the atoms. So think of the molecular geometry as just being the shape of the atoms that they adopt in the molecule. And it's really should be visual. If you can't visualize it, it's going to be hard to name these things. We're just memorizing them. But it should be octahedral electron domain, and then square pyramidal molecular geometry. If we have a molecule that has all bonding domains, then the electron domain geometry name is the exact same name as the molecular geometry. All right. Consider the polarities of the molecules below. Which ones, if any, are nonpolar? And so what we want to do here is try to think of, like when I have something like CO2, this is nonpolar because my bond dipoles cancel each other out, is one way of thinking of it. And then also another way of thinking of it is our molecules very symmetrical. We have the charge canceling itself out on the one side versus the other. And so for SF2, I have a lone pair, two lone pairs on sulfur. Fluorine's going to be bent in this case. We're kind of talking about this earlier. So we have a bent bond here. So I have these dipoles pointing down towards the more electronegative fluorine. So I have this big negative charge on the bottom half of the molecule, big positive charge on the top half. So this molecule here is going to be polar, therefore it's not nonpolar. Okay, so this is not an answer to the question. SF4. So SF4 is 6 plus 28, that's 34 electrons. So that's going to be sulfur, fluorine, fluorine. I'm already thinking of the geometry here. I have 8 electrons on each of the fluorines. There's 4 of them, so that's 32. The 2 left over, lone pair. So lone pair take one of the spots in a trigonal bipyramid electron domain geometry. And so then my actual geometry name here would be seesaw. And then I have this negative charge building up over here that's not countered on this half of the molecule. So having electron pair here, I would have to have something like SF5, where I have exactly 5 fluorines on this molecule. Maybe a molecule that does this is like PF5. If I had PF5 in this geometry, that would be nonpolar, but SF4 would be polar, would have a dipole moment. SF6, so if I have SF6, this fits that octahedral domain. So I'm going to sketch kind of a square pyramid here, and then I have a fluorine sticking straight out of the page, straight into the page. So if you put your pencil right on top of the sulfur, imagine that's where the fluorines are here, going into and out of the page. That this molecule here, perfectly symmetrical, all these bond dipoles. You imagine this dipole here cancels itself out. We have a dipole here and here, cancels out, dipole here and here. So if you think of dipoles as vectors, if they cancel each other out, then the molecule ends up being nonpolar. So 3 is nonpolar. PF3 is not going to be polar because I have 5 plus 3 times 7, that's 26 electrons. So again, I'm going to have an electron pair. Write the right atom. So we have phosphorus. The fluorines here are going to adopt that trigonal bipyramidal geometry, electron pair. So this molecule here is certainly going to have negative charge that's not canceled out by the electrons on top. Now, sometimes students are confused when you see that the fluorine should have a partial negative charge because they're more electronegative than phosphorus. You may think, well, electrons are negatively charged, which they are, but the charge resides on the nucleus. Think of the nuclear charge. The nuclear charge on this molecule is not positive. The electrons don't have enough negative charge to cancel that positive charge out on phosphorus. What we would need to cancel that positive charge out on phosphorus is another fluorine atom right on top of it, which we don't have. So this molecule here is polar and hence not nonpolar. PF5 we mentioned earlier, this would be the trigonal bipyramidal nonpolar molecule. So we'd have the fluorines, bond dipoles would cancel towards the fluorines, and then we'd have fluorines on the equator of the molecule, all with their dipoles canceling out too. So if you had a trigonal planar molecule like BF3, nonpolar, trigonal planar, PF3 here cancels out. The linear connection of the atoms also cancels out. So we should have 3 and 5 here as polar, as nonpolar, and the others as polar molecules. Now think of polar molecules. When a molecule is polar, it's going to have like a built-in attraction for itself. It's going to have the built-in positive side and a built-in negative side. A nonpolar molecule, despite having the bonds that are polarized, where we do have positive charged atoms, negatively charged atoms, we do have these charged centers in the molecule. We just don't have like 2 adjacent molecules that can have that built-in attraction for themselves. So nonpolar molecules, we're going to see in chapter 11 when we talk about liquids, that nonpolar molecules have a weaker attractive force for each other because they don't have these like built-in charges, if you will. And then if we have 2 polar molecules, they're going to have like a built-in stronger attraction for themselves because they have like the inherent ability to kind of sense the positive or the negative charge in each other. Another thought would be if you take a nonpolar molecule and you put like a positive or negative charge near the molecule, it's just going to kind of like spin. It's not going to necessarily flow towards or away from the charge. It's not going to know what to do with the charge. It's going to have part of its molecule that wants to flow towards the charge, another part of the molecule wants to flow away from the charge, and nothing's going to really win. If you put a charge in front of a molecule like, say, water, where you have this big negative charge on O, the positive charge is on H, if you put a negative charge, the H's are going to fly towards it and going to have that built-in attraction. The water molecule is going to flow towards the positive charge. If you flip the charge to negative, it's going to want to flow to that, or flip the charge to positive. Then the oxygen atom is going to want to sense that charge and be attracted towards it and flow towards it. So you can think about how a molecule would respond to charges as well to maybe help understand the difference and why we classify molecules and why it's important to think of them as being polar versus nonpolar. What are the bond angles in this molecule here? So when we see a Lewis structure that's two-dimensional like this one here, you have to think the 3D shape has to be interpreted. So like you can't just look at this bond angle for 8 and say it's 90 degrees. Not necessarily. What I have to look at this carbon here and see that the first carbon has 4 total domains. So that carbon is going to have to be tetrahedral. So that carbon will really look more like this. And then my bond to nitrogen, this one here is really truly linear like it looks. That's really 180 degrees. So 7 is truly 180 because if I have 2 domains total, they have to get 180 degrees relative to each other. So 7 is definitely 180. But angle 8, this should be described by having 4 domains. This should be closer to 109.5 degrees. And all these angles here should be about 109.5 degrees. So if 109.5 degrees is X, same bond angle around the molecule, approximately. So the answer should be C. Question 7, how many double and triple bonds does the molecule CH2, CH, CCH have? Well, just consider this connection here. Take CH2, take to CH, and then go to C, and then go to C, and then go to an H. Now, whether or not you draw these H's up or down, don't worry about that too much. Worry about the next step being, give 4 bonds to carbon. So think of it this way: carbon, 4 bonds, or let's say, think about how many bonding domains and non-bonding domains a given atom tends to have a 0 overall formal charge. So for carbon, that would be 4 bonding domains, 0 non-bonding domains. And so in other words, give carbon 1, 2, 3, 4 bonds each with no lone pairs of electrons. If you have hydrogen, it's really easy. Just give it 1 bonding domain, no lone pairs. So that's really obvious. We do that a lot of times. If we have nitrogen next to carbon, nitrogen likes to have 3 bonding domains, 1 lone pair. That gives it a 0 formal charge, like NH3. So if you have NH3, you have a lone pair on nitrogen. So 3 lone pairs, or 3 bonding domains, 1 non-bonding domain. If you have an oxygen, 2 bonding domains, 2 non-bonding domains, like water. And if we have something like fluorine or a halogen, it likes to have 1 bond with 3 non-bonding domains. And these are the count that give these atoms a octet satisfied and a 0 overall formal charge. Okay, so if we use that as our kind of guide, the next carbon is good because we have 1, 2, 3, 4. Its octet is satisfied, so we have 4 bonds around the next carbon. And so we move on to the third carbon and say, how do I satisfy its octet? We don't want to do it with lone pairs. We just do it with non-bonding, with bonding domains with bonds. We make a triple bond. And so without knowing the structure of the molecule, we can interpret the structure from just what it has to be in order for this molecule to be charge neutral, in order for it to satisfy its preference for bonds to carbon, 4 bonds to carbon. So we can come up with this Lewis structure here, hopefully pretty straightforwardly. So I end up with a double bond and a triple bond. And the other bonds are single in the molecule. Now, if you look at this bond here and say, well, why don't I do double-double? Why don't I do, why would this be wrong? Well, that's too many bonds to those carbons, so we can't do that bond there. So you just kind of think, give carbon 4 bonds, no more than 4 bonds, no lone pairs in common stable organic molecules. The central atom in which molecule below is described as being sp3 hybridized. So sp3 hybridization is what we observe in molecules that are tetrahedral in electron domain. So we're looking for a molecule that's tetrahedral. CO2 is linear. PCl5 is trigonal bipyramidal. CCl4 is tetrahedral. BeCl2 is linear. BCl3 is a trigonal planar molecule. So now carbon tetrachloride works because the molecule has 4 bonds to chlorine, no lone pairs on carbon, and so the molecule fits the bill of being perfectly tetrahedral, being described with 109.5 degree bond angle. So the idea here is that carbon has access to the full second row set of orbitals, so the 2s, 2px, 2py, 2pz. So if all 3 of those orbitals, so if we take what looks like these orbitals here of carbon and then hybridize them, we can take those orbitals, mix them together, and change them into orbitals that point in the direction of a tetrahedron. This is a bonding model. Atoms don't do this at all, but it's a model that helps us understand the bonding in these types of molecules. It's something that's maybe used more in OChem, or you'll come back to this model in OChem. So if I look at the carbon-chlorine bonds in CCl4, what I can say is that the bond here, I would say that this bond is the sp3 on carbon bonding or overlapping, that the orbitals result from the overlapping of atomic orbitals according to hybrid orbital theory and valence bond theory. And so sp3 on carbon overlapping with the 3p orbital of chlorine. So chlorine, its largest orbitals are 3p orbitals. So you take the largest orbital on the atom chlorine, overlap it with that of carbon. If we do one more quick example for BCl3 and say, well, how do we describe these bonds here? We have boron, chlorine, chlorine here, no lone pairs on boron. So we have lone pairs around the chlorines. The way we describe the bonds here would be that boron only needs to mix 2 of its p orbitals with an s, because what I need for boron here is I need to come up with 1, 2, 3 bonding domains or 3 bonds that it can form. So I take the sp2. So I take just 2 orbitals from the p shell and 1 of the s, mix them together. So take what looks like this, those p orbitals there, mix those together, and change their shape into something that looks like this. And so then I have 3 orbitals pointing in the direction of a trigonal plane, and I can get overlap here. So this would be sp2 of boron overlapping with the 3p of chlorine. So to answer this particular question, the sp3 atom is in CCl4. Which bond angle is greater according to Vesper theory? The bond in ammonia or the bond in methane? So the issue here is that in methane, the bonds are perfectly tetrahedral, so exactly 109.5 degrees. But in ammonia, we have this lone pair compressing these bonds together. So these bonds should be about 109.5 degrees in methane, but the bond pair here is closer to the nucleus, so it has a greater repulsion, pushes the bonding pair electrons closer together. So the bonding pair here ends up being a little less than 109.5 degrees. So CH4, its angle is greater. The bond in pH3 or the bond in BH3. BH3 is 120. The bonds in pH3 are closer to 109.5 degrees, and again, a little less than 109.5 degrees. And BH3, perfectly 120. So the BH3 bonds went out, so I got CH4, and then I have the BH3 bonds. And so what about formaldehyde? So C double bond O, hydrogen, hydrogen. The double bond repels this, is repelled by the single bond to a greater extent. So the single bond, there's less electrons in the single bond, so they can push closer together. So I can get this bond angle here to be a little less than 120, and this bond angle with the double bond, single bond to be a little greater than 120. So the O to the C to the H bond in formaldehyde is greater in angle. So it should be answer A. How many total sigma and pi bonds are there in this molecule? Well, let's just think real quick of hybridization. I have sp here, sp here. All these atoms here sp hybridized. I would have a lone pair on nitrogen. So like my nitrogen atom would have an sp hybridization. Carbon here, sp hybridization. This carbon sp hybridization. This carbon sp hybridization. This carbon sp hybridization. This carbon sp hybridization. So I get 1s sp3 overlap here. But then my triple bonds here are using these leftover p orbitals that's not hybridized. So I have plus p. So I have two p orbitals on carbon. So here's one set of those, and then here is another. So I have two sets of orbitals here that can overlap, and then the same thing here. I have two orbitals here that can overlap, and then I have these two that can overlap. So my single bonds is a sigma. So each of the times I have a single bond, that's a sigma. And each time I have these pi bonds, oh, it's getting messy, it's a sigma plus 2 pi. Sigma plus 2 pi. Sigma plus 2 pi. So I have a total of 6 pi bonds here. Then I have a total of 1, 2, 3, 4, 5 sigma bonds. Maybe I counted the sigmas wrong. 1, 2, 3, 4, 5, 6 sigma bonds. 6 sigma, 6 pi. Which molecule has the longest carbon-carbon bond? And so we have C2H6 single, we have C2H4, which is double, and we have carbon triple. So this bond here is the shortest of these three, and the carbon-oxygen single bond is the longest. The double bond should be right in the middle. For putting electrons into orbitals here, these are our 2s orbitals that are overlapping with each other. These are our 2p orbitals, and then we get our bonding orbitals in the middle. We get our sigma 2s, sigma star 2s. These orbital diagrams are given to you on exams. The pi 2p bonding orbitals, the sigma 2p, these are the thought of, okay, you have a given atom that has, s orbitals, so you get the s overlap kind of first, that's here. And then you have your p orbitals that can overlap, and you get two different types of overlap. You get your sigma overlap, that's here, and then you get your pi overlap, which is here. And then the pi overlap, there's the doubly degenerate set of orbitals. There's a second orbital that looks exactly the same. So whenever you have two orbitals that are equal, those are your pi set of orbitals. And so the issue here is that when you're filling electrons into something like, say, C2, that once you put two electrons here, it's hard to put two more electrons between the nucleus of the atom, so you use the pi bonds next. And then when the atoms become more highly positively charged, then you can start filling electrons first into the sigma 2p. So you just get a change of the order of these two orbitals between B2, C2, N2, and O2, F2, and neon 2, and ions of those atoms. So here we'd have our sigma 2s, sigma star 2s, sigma 2p, then pi 2p, then pi star 2p, the antibonding orbitals, and sigma star 2p. So your constructive interference goes down, your deconstructive interference goes up. So, and this is just from the idea in physics that if you stabilize something, you have to destabilize something else. If you stabilize an orbital, you have to destabilize an orbital. And it turns out you destabilize the orbital more than you stabilize it by. So the amount you go down, the orbital goes up by more. So the antibonding technically goes up higher than the bonding orbital goes downward. But anyway, so according to their molecular orbital diagrams, which molecules below is paramagnetic and hence would be drawn into a magnetic field? Well, the answer is actually O2, and we saw this in class, like in a picture. Sometimes I would do the demo of it, but it's a pretty boring demo. But oxygen's pulled into a magnetic field, and that's actually what leads us into this whole topic of needing to understand why a Lewis structure we sketch like this somehow has lone pairs of electrons. You have lone pairs of electrons because we don't really understand so well with the Lewis structure what's going on with all these electrons. If you throw the electrons into your diagram for O2, you'll see 2, 4, 6, 8, 10, and 12. I'm just putting my 2 times 6 electrons in for O2, so 12 electrons in. I end up with 2 unpaired electrons. Now, like the electrons that go down then up, those result in non-bonding electrons. So it's like 2 down, 2 up. That's maybe these 2 sets of electrons here. Then we make 3 bonds, but we cancel out 2 of the pi bonds with electrons. And so I think the issue would be that we just end up having oxygen looking maybe something more like this, where we have oxygen kind of like this, where we have electrons paired in the same direction, and then these two are spin paired. Very confusing on how you might picture this, but you have a net double bond still, so the double bond was right, but we're just seeing that the electron pairs really aren't paired up. as lone pairs on the central atom. And you can kind of see that as an artifact of this MO diagram. So we have spin unpaired electrons in O2. F2 would spin paired two more electrons, so that would be spin paired. C2 would have this diagram here with all electrons spin paired, and N2, two more electrons, all those electrons spin paired. Spin paired is diamagnetic, spin unpaired is paramagnetic. Using their bond orders is determined from their molecular orbital diagrams. Arrange the bond lengths in order for the following molecules: O2, B2, and N2. So we're trying to put these molecules in order of bond length using their bond length trends that we get, or their bond orders we get from their MO diagrams. Okay, so we're going to put B2 into our diagram here. Boron has 6 valence electrons, so again, our 2s and our 2p. So we go 2, 4, 6 electrons. So B2 would be paramagnetic because it has 2 unpaired electrons. It would have a net bond order of just 1. Because we have 4 bonding electrons minus 2 anti-bonding electrons times a half. So that's where we get the 1 from. O2, 2, 4, 6, 8, 10, 12. And so I'm going to circle the anti-bonding electrons. So I have 4 anti-bonding electrons for O2. So I have a total of 12 electrons to put into the diagram. Also ends up being paramagnetic. And then our bond order will be, a half times our 8 bonding electrons minus the 4 anti-bonding. So the bond order is 2, just like we would have thought from the Lewis diagram. So double bond. N2 over to this diagram here for N2, 10 total electrons going in. So I just need to complete my diagram with 4 more electrons than N2. And so that's been paired in terms of our electrons. So that's diamagnetic. And then the bond order would be equal to a half times 8 bonding minus 2 anti-bondings for 3. And again, just like we would have expected from its Lewis diagram too. And so boron should be the longest, O2 in the middle, and N2 the shortest. So we're just taking the triple bond is shorter than the double bond is shorter than the single bond. So N2 less than O2, less than B2. So when we're comparing atoms that are all single bonds or all double bonds, we use atomic radii trends to rank their bond lengths. But when atoms are different in bond order, we use their bond orders to rank their bond length trends. And this works whenever the atoms are in the same row of the periodic table as each other. So we couldn't compare, like an oxygen-oxygen double bond to like a sulfur-sulfur single bond or something like that in mixed rows. So within the same row, triple, shorter than double, shorter than single. Then our last question on the activity, which Lewis structure is most consistent with the molecular orbital diagram of C2? Now C2 is an interesting molecule. If I had just said from chapter 8, how do you sketch the Lewis structure here? You would probably go with this one here, because in chapter 8 we said for a diatomic molecule, if you can, satisfy the octet rule for both atoms. And so that would be a quadruple bond, because that would give each atom a 0 formal charge, and it would also give each atom a completed octet. Now when we look at our MO diagram for C2, we can try to put in our 8 electrons for C2. So I'm going to put 8 electrons in, 2, 4, 6, 8. And so something really interesting, the two really interesting things happen. One of those is that we have an anti-bonding orbital. Now the idea here is that what this orbital looks like, in this orbital too, what these orbitals look like is carbon is putting its s electrons into the center of the molecule for constructive interference for the 1. That's this orbital here. And then this orbital here, the carbon, is kind of breaking that bond. It's putting the electrons far away from the nucleus, and you have this like node in the middle. And so you're breaking the bond that you're trying to make, and so then you have the electrons far away from the nucleus. Bonding orbitals put electrons between the nuclei. Anti-bonding orbitals put the electrons away from the nuclei. So this is our sigma star, and this is our sigma bonding orbital. And so the net effect that has is that creates 2 lone pairs of electrons. So the average of a bond being made and a bond being broken is lone pairs. And so then we end up with a molecule that has two net bonds. I don't know why I erased that. We have two net bonds here, these here, and those net bonds turn out to be pi bonds. So we have a little structure I would sketch that's more like this, and then those two bonds there happen to be two pi bonds because the net bonds are actual pi bonds, meaning that the two bonds there look more like this and like that. So we still, on average, have electrons in the middle of the atom. It's just they're being broken by the antibonding electrons outside the atom. So when we think of non-bonding electrons, they're a little bit more complicated than just being like dots on an atom. Those electrons are kind of the effect of trying to make a bond, but then trying to break the bond. So the net effect of going up and going down by an equal amount is just the result is really no net bond being created by those interactions. Okay, so that takes us through this activity. Hope you have a great week.